Alright, in this section we're going to talk about the use of cylindrical coordinates as well as spherical coordinates. You'll remember from trigonometry, pre-cal, and use of in Cal 1 and Cal 2 that we have other ways of expressing points on the plane. One way to express a point on a plane is, of course, to simply use the XY coordinate system, where to find a point, you simply give directions from the origin, how far left or right you want to go, and how far up or down you want to go. So, for example, here I could go one step to the right and one step up, and that would be the point 1, 1. However, the other thing I could do is I could say, well, starting from the origin, which direction is that point in? Well, in trigonometry, we define angles in a positive direction, going this way, counterclockwise. If this is 0, this would be pi over 4. Right? 0, pi over 6, pi over 4, pi over 3, pi over 2. So we would say, okay, what's this angle? And then how far forward do you want to go to get to that point along that angle? So here, this would be in rectangular coordinates. On the other hand, you could also have that be the point in polar coordinates, where in this case you would have r and theta. R being the square root of 2 and theta being pi over 4. Right? There was a way to convert back and forth between these, and it was simply a result from trigonometry. You'll remember that a parameterization, a way of expressing points in the xy plane with respect to the angle, was given by x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. So here we had ways of converting back and forth between rectangular and polar coordinates. But this is on the plane. Now we're talking about a three-dimensional space. Well, it turns out we can still do the same thing. Because when you talk about a three-dimensional space, yes, you can give a point by giving its directions in the typical Euclidean fashion. Meaning, tell me how far left or right you want to go, how far back and forth you want to go, how far up and down you want to go. Instead of having an x and a y, you'd have an x, a y, and a z. But it would still have the same it will still be the same idea, yeah? All right. So, how do I get from here to this point up there? Well, I could take one step along the x-axis, and I could take 2 steps along the y-axis, and I could take 1, 2, 3 steps above in 3 steps along the z-axis. Right? 1, 2, 3. Oh, this would be the point 1, 2, 3. 1 step, and then 2 steps, and then 3 steps. 1, 2, 3. But that's not the only way to get to that point. We could use an angle. Well, how do we want to do that, though? I mean, yeah, I guess we can talk about the angle from here to here. We did talk about reference angles. We did talk about direction angles in a previous section. So we could give the angle with reference to the x-axis, the y-axis, and the z-axis, and that'll give me that. But why am I making that so complicated? Couldn't I just find down here on the xy plane and then just come straight up? Well, it turns out both of those are perfectly valid. And it gives rise to 2 different coordinate systems, different from the regular Euclidean, the rectangular coordinate system. Sorry, not Euclidean, Cartesian. Euclidean means something else. Different than the typical Cartesian coordinate system, the typical XYZ system. Those are going to be called the rectangular. This one's called the rectangular coordinate system. The other 2 are called the cylindrical coordinate system and the spherical coordinate system. Just like polar and rectangular, they're not really a different space. They're just a different label for the same point. However, just like with rectangular and polar, we saw in Cal 2, then sometimes it's useful to have something written one way, sometimes it's useful to have things written the other way. Sometimes it's useful to have things in the XY coordinate system. On the other hand, sometimes it was easier to parameterize. So how do we do that? How do we convert back and forth? So first of all, we want to talk about what those coordinate systems are. Like, what am I talking about? If I give you a number or two numbers or three numbers, what do they mean? Here, 1, 2, 3, yeah, I get that. 1 step in the x direction, 2 steps in the y direction, 3 steps in the z direction. But what does it mean to have, a number or numbers in these new systems? So, definition. We're going to start off with a point in space. Let P be a point in space. Okay. Then P can be represented by the ordered triple r theta z in the cylindrical coordinate system. We'll talk about spherical next. With r and theta, it's not a coincidence we use the same symbols as above. Those mean the exact same thing that they did in polar coordinates. Here, r and theta as the polar representation of the projection. Don't worry, you don't actually have to compute projections for this. Of the projection of P onto the xy plane. And z, the directed distance from r theta to P. So what we're defining here is the cylindrical coordinate system. And then there's another part to this definition. It's a very small part. In this system, the point 0, 0, 0 is called the pole. All right. So here's a formal definition. Somewhat informally. Here's what it's saying. You want to get to that point, right? Yes. But you don't want to use the XYZ coordinate system. You don't want to say 1 step along the x-axis, 2 steps along the y-axis, and 3 steps along the z-axis. That's right, I don't want to do that. Okay, here's another way you can designate that point. Take this point and bring it down until it's sitting on the xy coordinate system, on the xy plane. Okay, I brought it down. It's right there. Now what? Well, now it's on the xy plane. You can use polar coordinates. Okay, so from the positive half of the x-axis, I can measure an angle. That's the angle theta. Okay, now that I know what angle it takes for me to get to here, I can figure out what distance it takes. Okay, the distance is r. Okay, I'm going to go forward. Notice that's exactly the same image that I have over here. Theta and r. Okay, so now my theta tells me what direction I'm facing on the xy plane. R tells me how far to go in that direction. So that gets me to that point right there, which we call the projection of P onto the plane. And we brought that straight down. Okay, but now that's not the right point. It's underneath the right point. We want to go up. Well, how far up do you want to go? Well, okay. I didn't want to use X, Y, and Z, but I guess I'm okay using just Z. Because here, this already gets me underneath the point I want. So let me just go straight up. Okay, so I'm okay with using Z, as long as I don't have to use X and Y. Hey, I'm okay with using Z. That's how the system works. R and theta gets you underneath the right point, and then Z picks you up to get to the right point up in space. This one is fairly simple because this R and this theta are identical to the R and theta we're used to, which means all the same conversion factors still exist. Here, to convert back and forth between rectangular and polar is really pretty simple. Cylindrical to rectangular. Okay, how do you find X using R, theta, and Z? You already know how to do that. R cosine theta, same one. How do you find Y? You already know how to do that. R sine of theta, same thing. And now here's a really silly one. Okay, from cylindrical to rectangular. What if I wanted to find Z? How would I do that? You don't need to find it. It's already given to you. Z is equal to Z. And there you go. Nice and simple. If you want to go the other way, rectangular to cylindrical. Then these are going to sound familiar as well. How do you find R squared? That's equal to X squared plus Y squared. How do you find theta? Well, we know the tangent of theta is equal to Y over X. You'll remember these from trigonometry. And again, how do you find Z? You don't find Z. Z is already Z. You just leave that alone. These conversion factors allow us to convert points to points and allow us to convert equations to equations. Meaning, I can get a point that's cylindrical and convert it to rectangular. I can get a point that's rectangular and convert it to cylindrical. Or I can take a whole equation that's cylindrical, convert it to rectangular, or from rectangular to cylindrical. So let's see some examples of those. Let's convert from cylindrical to rectangular. Let's start off with a point. 6 comma negative pi over 4 comma 2. Okay. By convention, unless there's some reason why we're stating otherwise, these are always stated in the order R, theta, Z for cylindrical coordinates, just like you would always state things as X, Y, and Z for rectangular coordinates. All right. So here, to go from cylindrical to rectangular, you want to find your X. That's equal to R cosine of theta. R is 6. Theta is negative pi over 4. Okay. The cosine of negative pi over 4. Cosine is an even function, so that's the same as the cosine of positive pi over 4, which is root 2 over 2. Multiplied by that 6, that's going to be 3 root 2. Y is going to equal to R sine of theta. And so that's going to be 6 times the sine of negative pi over 4. Okay. Sine is an odd function, so the sine of negative pi over 4 is the opposite of the sine of positive pi over 4. Or in other words, it's negative root 2 over 2. Times 6, that's negative 3 root 2. Okay. And finally, Z equals Z. That's always a nice one, which is just 2. So that means that if you convert this from cylindrical to rectangular, you end up with 3 root 2, comma 3 root 2, comma 2. Converting from point to point is not exactly exciting. It's not exactly anything groundbreaking. However, we will need to occasionally convert from one system to another, especially when we start talking about integration in these systems. We know how to integrate in terms of x and y. How do you integrate in terms of something like this? Well, it's going to be very similar. But just like when you perform a substitution, your x turns into a u or a theta or something like that. When you perform a substitution in Cal 2, you also change your boundaries. Same thing here. If your values change, if your coordinate system changes, then that means that your values will also change to that new coordinate system. Right? So we will occasionally need to do this when we consider integrations. Now, you don't just convert points to points. You might also convert equations to equations. So for example, let's consider z is equal to r squared cosine squared of theta. Okay. To convert to rectangular, again, we're using all of this stuff. Anytime you see a z, you're just going to leave that alone. Okay, but now sines and cosines of theta, r sine theta, r cosine theta, those will turn into x and y. Notice that r squared cosine squared of theta is really just the square of this. You could write this as z equals to r cosine of theta quantity squared. That would square each of those factors. But since r cosine of theta, since r cosine of theta is x, you could then write this as z equals to x squared. So this becomes this, which becomes this. Oh, and there we go. That's a rectangular equation in the rectangular coordinate system, x, y, and z. You might try this one. Let's say you had r equals to 2 times the cosine of theta. Now remember, when we convert, r cosine of theta is equal to x. That is not r cosine of theta. You can't say, oh, r is equal to 2. No, 2 is a constant. R needs to be a variable. So try this. Think about this for a moment and see if you can convert this into a rectangular equation. Go ahead and pause and give yourself what time you need. And once you're done, go ahead and unpause and we'll go through it together. Okay. I need an r here. I can't convert into x or anything else right now, the way this is written. But if this had an r cosine of theta would be equal to x. Okay, well, let me multiply both sides by r. Times r times r. That would give me r squared equals 2r cosine of theta. Okay, well, r cosine of theta, that's equal to x. And notice that r squared is the sum of the squares of x and y. So here, that, once I multiply by r on both sides, becomes this, which now I can convert. R squared is equal to x squared plus y squared equals 2 r cosine theta. Or in other words, 2x. And there we go. This is a rectangular equation, and in fact, this is a cylinder. Notice that you have a rectangular equation, but you're missing your z coordinate. This would be a cylinder with rulings that are parallel to the z-axis. In fact, this one is as well. Here you would have a y missing, which means you'd have a cylinder with rulings that are parallel to y. So both of these are cylinders. Notice this generating curve is a parabola, so you would have a parabola that would generate the cylinder in the direction of the y-axis. And here this is a circle, which would give you a much more traditional looking cylinder, an empty hollow tube. Of course, you may have to go back in the other direction. So let's consider an example. Instead of from cylindrical to rectangular, let's consider now rectangular to cylindrical. Okay. Let's consider, first of all, just like before, let's take a look at a point. 3, comma, negative 3, comma, 7. All right, so this is rectangular, so x, y, and z. And we're going to convert this into cylindrical. So we're going to need to find our r and our theta. We already know our z. So in fact, let's do that one first. Z equals z, which is 7. Okay, great. No need to worry about that anymore. We need to find our value of r. Here you note that r squared equals x squared plus y squared. So here we'll have r squared equals x squared. Oh, I suppose I should actually write that, right? X squared plus y squared, which in this case would be 3 squared plus a negative 3 squared. And it'll give us 18, which means that r must equal to the root of 18, which we can simplify. That would give us what? 3 root 2. Just like that. And then theta, we know that the tangent of theta is given by y over x. And again, that's something that we see since trigonometry. Tangent of theta is equal to y over x. And here, that's negative 3 over 3. Like that, which is just negative 1. Which implies that theta must equal to the arctangent, the inverse tangent, whichever you want to call it, the arctangent of minus 1. And the arctangent of minus 1, that's negative pi over 4. We can also do degrees, but this is, by convention, all these things are being done in radians anyway, so I'll stick with the convention. So here, from rectangular to cylindrical, we have our r, we have our x, we have our r, our theta, and our z. And of course, by convention, we put those in that order. R, theta, and z. And that's our result. There's a little word of warning here. Note that when we have r squared equals 18, we said r is equal to the root of 18. Now those two are not equivalent statements, right? If r squared is equal to 18, r is not necessarily the root of 18. It could be plus or minus the root. So how do I know that's a positive root? Look at just x and y. Forget about z. Z is simple enough. Z is going to stay z. So just look at x and y. On the xy plane, this will go 3 steps to the right and down 3 steps. Right over here. Okay, that's 3 comma negative 3. All right, so to get to this angle here, I would go negative pi over 4. Okay, so from here, instead of going pi over 4 in the positive direction, counterclockwise, I would go pi over 4 units in the negative direction, which would be clockwise. Okay, so now if I'm facing this way, of course I'm going to go forward. I'm already facing in the right direction into the right quadrant. Remember that the arctangent can only give you things either in the first or the fourth quadrant, from negative pi over 2 to positive pi over 2. Right? The range of the arctangent is not all the way around. It's simply from negative pi over 2 to positive pi over 2. So that means if you had something back here, then you wouldn't be able to face in that direction. So for example, let's say instead of 3 comma negative 3, let's say I had it the other way around. Let's say I had negative 3, 3. So that would be 3 steps to the left first, and then up by 3. Something like that. Well, I would still have tangent of theta is y over x. I would still have tangent of theta is 3 over negative 3, even though the negative is in the denominator now. So what? It's still negative 1. So I would still have an arctangent that's negative pi over 4, putting me down here somewhere. The problem is, that's the wrong direction. So I can't go forward to get to that point. Oh, but notice it's just facing the opposite direction. Okay, so I should go backwards. Oh, okay. So in that case, I would use r is equal to negative root 18. So be mindful of that. It's saying r squared is equal to 18 does not automatically mean r is the root of 18. Here, that was the case because I could walk forward along this angle to get to my point. However, if I was facing in the wrong direction. In this case, the value of r would be negative. Here, r can be positive or negative. It can be directed in either way. So be mindful of that. In this situation, here r is greater than 0. However, you might end up with a negative root in this case where r is less than 0. You will end up with a negative root. So just be mindful of that. This from trigonometry has not gone away. And just like in the previous examples, we can convert from rectangular to cylindrical in terms of points, or we can convert from rectangular to cylindrical considering equations. So let's consider an example of that. Thankfully, converting from rectangular equations to cylindrical equations is actually really, really straightforward. You might, for example, consider y is equal to x squared. It's a cylinder, because here you're missing the coordinate z, so you would have a cylinder with rulings that are parallel to the z-axis. But regardless of what it looks like, it would be, well, I know what y is. Y is equal to r sine of theta. And I know what x is. X is equal to r cosine of theta. Well, the whole thing is squared like that. Okay, I can expand this out a little bit. I can write this as r sine of theta equals r squared cosine squared of theta. Like that. Okay. Here, that's the correct equation. However, oftentimes we try to write things as a function, just like we often try to write y as a function of x if possible. Here, if possible, we like to write here r as a function of theta. Here, as long as x is not equal to 0, so we should probably make a note of that. As long as x is not equal to 0, as long as r cosine of theta is not equal to 0, we can divide by it. So that would be over r cosine of theta, r cosine of theta. Here the r's divide away, and again, we're assuming that this is not 0. Sine of theta over cosine of theta would be tangent of theta, and this would be equal to, these would divide out to give me r cosine of theta like this. And then again, assuming that none of this is equal to 0, we could then divide on both sides by cosine of theta, or if you prefer, you can use the reciprocal function, the secant of theta. Cosine of theta times secant of theta. These are reciprocals. They would give you the number 1. Do the same thing on the other side. And so we get r is equal to secant of theta tangent of theta. Here, assuming that the value of r and the value of cosine of theta was never equal to 0. Assuming r cosine theta was never equal to 0. Or over here, basically, assuming that x was not 0. So here, we can convert from rectangular to polar, and thankfully it's usually pretty straightforward, because all you really have to do is anywhere I have a y, I put in r sine of theta. Anywhere I have an x, I put r cosine of theta, and then expand and simplify. Should you have any z's, those will stay exactly as they are. Now the next part of our section begins with the definition of another coordinate system. We've seen rectangular in previous sections. We see cylindrical here, which is really just polar with one extra lift. Push things straight up along the z-axis. However, this one that we're about to see is somewhat different. So let's begin with a point. Let P be a point in space. P can be represented by the ordered triple might say, what are those symbols? Is that the letter E or is that the letter P? That's neither of those. Here, these are pronounced as rho. These are Greek letters. Rho, theta, this is the theta that you're familiar with. And it's not a coincidence that we're using theta. Again, it's the same theta that we're used to from polar coordinates, from cylindrical coordinates. Theta. And then this is phi. It's a little circle with a line straight up and down the middle. This is read as rho, theta, phi. Where rho is the distance between the point and the origin. Because it's a distance, it has to be positive. So rho needs to be greater than 0. Or I suppose it can be equal to 0, right? You can actually be right at the pole. So rho should be greater than or equal to 0. Theta, that's going to be the same as the one using cylindrical coordinates. Same as used in cylindrical coordinates. For r greater than or equal to 0. Not that there's an r in this coordinate system, but if you are in cylindrical coordinates and your r is greater than 0, that's what we're talking about. In other words, it's the positive oriented angle where you're pointing directly to where you're under the point that you want. And then phi is another angle. This is the angle between the positive half of the x-axis not x-axis, z-axis, and the vector from the origin to the point that we care about. Here, this angle should always be positive. Or I guess I should say greater than or equal to 0. All of these can equal to 0 if we need them to. Before we get into computational stuff or conversion stuff, what is this? What is rho, theta, and phi? Well, there it is, right there. It's defined. Okay, can you draw us a picture? Well, I think the answer is no, because, well, you've seen me draw. But, well, I'll do my best. Okay, so here is the x, y, z coordinate system. And if I was going to draw something on here, I could get there by taking one step in the x direction, and then maybe 2 steps in the y direction, and then maybe 1, 2, 3 steps in the z direction. So something like that. 1 step, 2 steps, 3 steps. One, 2, 3. Okay. Now, another way of getting there is, as we saw before, using basically polar coordinates to get me right under my point and then coming straight up. The third way to do it is right here. We're going to use 2 angles. One angle is the traditional theta that we've seen all the way back since trigonometry. That theta has an initial ray that's along the positive half of the x-axis. And it's the theta that would put us right underneath our point. So that's theta. Okay? But that's not enough. Right? I need more information because this will put me right underneath. But I don't have a z in this coordinate system, so I can't just end up underneath my point and then come straight up. I also need something else to tell me how far up I am. Well, instead of a distance, we're going to use a second angle. That's what phi is. Phi is the angle between the positive half of the x-axis, so this is the initial ray, and the vector OP, where O is the origin and P is the point that we're trying to get to. So OP would start from the origin and go to P, like this. And so phi is this angle right in here. So you have two angles. One angle gets you the right elevation. The other angle gets you that elevation pointed in the right direction. Between those two angles, you know you're going to end up somewhere up here. Oh, but where up here? After all, this is a vector. It keeps on going forever. Oh, sorry, this is a vector. This is a line. It keeps on going forever. So just because I know the direction vector doesn't mean I know where I end up. Oh, that's what rho is for. Once I have this angle, that gives me an elevation. And once I have this angle, it tells me what direction that elevation is facing. Well, then now I need to know how far to go in that direction, and that'll get me my point. So that's what rho is. Rho is the distance from the origin up to the point P. Or in other words, rho is the magnitude of OP. So those three numbers, two angles and a distance, get me to the point just as well as X, Y, and Z would. We're going to have some conversion factors, just like we had X is equal to R cosine theta, Y is equal to R sine of theta, and such. We're going to have some conversion factors for spherical and rectangular coordinates as well. So how do I go from spherical to rectangular? Okay, so how do we find X? X is going to be rho sine of phi cosine of theta. How do I find Y? Y will be rho sine of phi sine of theta. That's kind of like saying your R cosine theta, R sine of theta. This looks very similar. Finally, here we see Z equals to rho cosine of phi. Like this. Going back from rectangular to cylindrical also has some conversions, which are, although not the same as with cylindrical and rectangular, do have at least a few similarities. So let's see, from spherical to rectangular, to go from rectangular back to cylindrical, to spherical. Rho squared is equal to, so thinking back to cylindrical, R squared is equal to X squared plus Y squared. Here, rho squared is going to equal to X squared plus Y squared plus Z squared. And here you could actually do that if you square all three of these and add them, you'll find that here all of these simplify out, and you're just left with rho squared. Tangent of theta is equal to y over x. That's exactly what we have with rectangular coordinates to cylindrical coordinates, because that's the same theta. Right? That's the same one used in cylindrical coordinates. And finally, we have that phi is equal to the, and this one's a little unexpected, is equal to the arc cosine of z over the square root of x squared plus y squared plus z squared. Incidentally, although it's not something we see much of, there is a way to go between spherical and cylindrical. Of course, one way is you could just say, well, if I want to go from spherical to cylindrical, I can just say spherical to rectangular and then rectangular to cylindrical. And actually, that's what this is. It simply does the algebra all at once. Right? So here, you can actually go forgo going through rectangular coordinates and just jump directly between one system and the other. So if you want to go from spherical to cylindrical, you would take r squared is equal to rho squared sine squared of phi. And that's really just what you would get if you took spherical to rectangular and then rectangular to cylindrical and completed all the substitutions. Here, theta is the same as in both systems. So here, theta is equal to theta. That's always the nice one. And then z is equal to rho cosine of phi. Like that. And going back the other way, oh, I seem to run out of space. Let's put it right over here. If you wanted to go from cylindrical to spherical, you could do that as well. You would have rho is equal to the square root of r squared plus z squared. And again, that's just what you would get if you took cylindrical to rectangular and then rectangular to spherical and completed all the substitutions. Again, theta is equal to theta. And then phi is equal to, and here you'll be seeing this one again right here. Phi is equal to, it's exactly this right here, except, I don't want x and y because I'm dealing with cylindrical to spherical. Oh, but x squared plus y squared is equal to r squared anyway. So here it's exactly this, but with this is x squared and y squared. So that's the arc cosine of z over the square root of r squared plus z squared. We don't see these used very much. We don't often have reasons to jump, at least in this class. We don't have reasons to often jump between spherical and cylindrical or cylindrical to spherical, but should that need ever arise, that's how you would do it. But for the most part, we're going to jump back and forth between rectangular and one of the others. So this is what we're going to see most often, as well as this set over here. All right, so let's see some examples of this, converting back and forth between rectangular and spherical. Let's go ahead and start by converting from spherical to rectangular. And as always, we're going to start off with a point, and then we'll look at an equation as well. A spherical coordinate would be something like 9, pi over 4, pi. Well, remember that by convention, this first one is rho, so it's the only one that's a distance. And then these are going to be theta and phi, rho, theta, phi. All right, so to convert into rectangular, we're going to use the fact that x is going to equal to rho sine of phi cosine of theta. Y is equal to rho sine of phi sine of theta. And z is equal to rho cosine of phi. And just plug everything in. So here our x is going to be 9 times the sine of pi. Okay, well the sine of pi is 0. Times the cosine of pi over 4. Now of course I know the whole thing's going to be 0, but just to be thorough, cosine of pi over 4, that's going to be root 2 over 2. But of course if you multiply all three of those, you're just going to get 0. y is going to be rho, so that's 9, times sine of phi, once again, that's 0, times the sine of theta, sine of pi over 4, that's also root 2 over 2, which of course gives us 0. And then z is going to be rho times the cosine of phi. Cosine of pi, that's going to be negative 1. So the whole thing will give us negative 9. So this point from spherical to rectangular will give us the point 0, 0, 9. It's just a matter of substituting these in the right places and performing the multiplications. With an equation, you'll have something similar, but instead of converting one point at a time, getting a number, we'll get a different equation. So, for example, let's say we have rho equals 4 times the cosine of phi. Well, let's see. Rho equals 4 cosine of phi. I see cosine of phi right here, but it needs an extra rho in there. Okay, so let me multiply on both sides by rho. So rho and rho. Row, row, row your boat. This is going to give us rho squared equals 4 rho cosine of phi. Oh, but rho cosine of phi, that's just z, isn't it? And then rho squared, we saw that a moment ago, didn't we? Rho squared is the sum of the squares of all 3 rectangular variables, x squared, y squared, and z squared. Yeah? So here, that's going to give us x squared plus y squared plus z squared equals 4 times rho cosine of phi, which is just z, like that. One thing, do not ever say, oh, here that's rho cosine of phi, and rho just happens to be the number 4. That's not how that works. 4 is a constant. Rho, phi, and theta are variables. That constant cannot be that variable. You'd have to have a separate variable in its place. Here, this is a perfectly acceptable answer. However, for many of the answers in this textbook, they often try to simplify them into some other form. In particular, this one, they'll often try to get something to be 0 on one side. So something like x squared plus y squared, or not necessarily 0, but they'll try to get it to be constant on one side. X squared plus y squared plus z squared minus 4z equals to 0. So now this looks an awful lot like a quadric, and in fact it looks almost exactly like a sphere, right? Except for that term right there. It turns out if we complete the square here, it is a sphere, and we'll see exactly what sphere that is. So here, this is probably the answer you'd want to give, but here I'm going to take this one step further. If you note right here, you can complete the square. You add 4 to both sides. You could factor this part down as z minus 2 squared is equal to 4. All right, if you add 4 to both sides, that is now a perfect square, which you factor down here. 0 plus 4 is 4. And now, x squared plus y squared plus z squared, that's the equation of a sphere centered at the origin. Oh, but that minus 2, oh, this will actually be a sphere. Centered at 0, 0, 2, with a radius of 2, the square root of that number. And radius 2. That's one thing you'll find, and which we'll take that full advantage of. The rectangular coordinate system naturally forms rectangular solids. One of the simplest things to form that happens effortlessly is you make boxes. The cylindrical coordinate system, one of the most effortless things to do is to make a cylinder. And in the spherical coordinate system, one of the most effortless things to do is to make a sphere. So in later sections, we'll start talking about solids, and we'll ask about volumes and surface areas and such. Depending on what your surface looks like, depending on what your solid looks like, you may wish to use a particular coordinate system. For example, let's say we're talking about something that looks like this. Let's say that's a paraboloid up there. And then it comes straight down this way. So the question would be something like, find the volume in here. Well, that's not a cylinder, except it kind of is. Right? Okay, it doesn't have the flat top up there, but everything else about it looks like a cylinder. So maybe, just maybe, this kind of a problem would be best done in cylindrical coordinates. It would be, quote unquote, effortless to make this kind of an object. When I say effortless, I mean the equation to make this object in cylindrical coordinates would probably be very simple. And simple equations mean I have simpler integrations and differentiations to consider. Likewise, if I had an object that looked something like this, where this was the upper half of a sphere, and the question was something like find the surface area or something of that nature, well then maybe spherical coordinates would be the best, because this equation, this surface would be very easily graphed in spherical coordinates, because these are naturally set up to work nicely with those. Notice here, this equation was a sphere. This sphere is using all three variables, and in fact the square of all three variables. Here you have rho is equal to 4 cosine of phi. You don't even have to worry about theta here. You don't even worry about all three variables. And here you just have one as a function of the other. Here, there's no function. I don't have x or y or z as a function of anything. So here, not a function, and everything is squared. Here, just rho equals a simple trig function. Well, this is going to be easier to work with than this is. So this is where we're heading with this. The three different coordinate systems are all equivalent. They all give you the same answers for everything, because of course they're all describing the same object. But if one describes an object in a simpler way than another, if one describes it in a more natural way than another, then those simpler equations are going to be easier to work with when we're looking for volumes, for surface areas, when we're integrating and double integrating and triple integrating and so forth. Now, that's not to say everything is always nicest in spherical or cylindrical. For example, go ahead and try this one. Go ahead and convert, same thing, from spherical to rectangular. Try rho equals 2 secant of phi. Go ahead and pause and convert. And once you're done, go ahead and unpause and we'll go through it together. All right, looking at this one, note that secant is the reciprocal of the cosine function. So if I just multiply by cosine of phi right here, that's 1. Oh, but whatever I do on one side, I do on the other side. So this will give us rho cosine of phi equals 2. Oh, but I know rho cosine of phi. That's z. So in this case, this one is significantly simpler. In fact, it's constant here. So in spherical coordinates, this is difficult to work with, at least compared to this. In rectangular coordinates, it only uses a single variable. It's a constant. In fact, if I were to graph this, it would just be a perfectly flat plane. Here z is equal to 2. X and y can be whatever, as long as z is equal to 2. So that would be this plane up here. That's 2 steps above the xy plane. Notice that you could think of that as being the top of some box. So of course that would be far simplest to describe in rectangular coordinates than you would in spherical or cylindrical coordinates. So that is our conversion. Finally, let's go back the other way. As our last examples, we've gone from cylindrical to rectangular. Let's go back rectangular to cylindrical, spherical. All right, let's start with the point. Let's see here. Oh, let's keep it simple here. Let's just convert the point -1 to 1. Okay. Again, this is rectangular, so that's your x, your y, and your z as always. And we need to find our rho, our theta, and our phi. Now remember, rho squared equals x squared plus y squared plus z squared. Okay. Now remember, when you take the square root of both sides, you would need a positive and a negative, normally. However, given the way that spherical coordinates are defined, note that rho is a distance, meaning it must be non-negative. So here, we don't have to consider the extra root. Here we can simply jump directly to, oh, that just means that since rho must be positive, that means rho is equal to the square root of x squared plus y squared plus z squared. And again, that's since rho must be non-negative. Okay, so there we go. Just plug in those numbers. That'll be the square root of -1 squared plus 2 squared plus 1 squared. So 4, 5, 6. That's the square root of 6. Okay, so when we convert to rectangular, from rectangular to spherical, we're turning x, y, and z into rho, theta, and phi. All right, so we have our rho. That's the square root of 6. Looking for theta. Looking for theta is the same theta that we have when we work with polar coordinates. So that one's been done to death, right? It's going to be the arctangent of y over x. Oh, well, that means that theta is equal to the arctangent of, let's see, what's our y? 2 over -1, so just -2. Okay. Here, you can actually just write arctangent of -2. That's a perfectly good number. If you really want to, you can always go and convert. You can always go ahead and use a calculator to give a decimal. But if you're going to do that, make sure you change your calculator to radians. We don't use degrees on any of these. This is not -2 degrees. Everything's in radians. So if you're going to take the arctangent of that -2, you'd get -1.1071. Personally, I would rather you just put in that right there, the arctangent of -2. And then finally, phi. Phi is given by, and that was that sort of strange looking one. That's going to be the cosine. Oh, sorry, the inverse cosine. I guess I should be consistent. If I'm calling this the arctangent, I should call the other one the arc cosine. It means the same thing. All right, the arc cosine of 1 over, well, actually it's z over. It will be 1 once I plug that in, but generally it's z over the square root of the sum of the squares of x, y, and z. Okay? So that one would be that phi is the arc cosine of, let's see here, that's going to be a 1 on top, and then down here, that's going to be the square root of this number over here that we had. Right? But that's that one we had over here, which was what, square root of 6? Okay, so it's actually not terribly difficult to remember then. It's really just arc cosine of z over rho, right? Where rho is this number that we computed before. Here, if you really want to, you can, of course, go ahead and type that into a calculator. Again, making sure that everything's in radians. 1 divided by square root of 6, and then we take the arc cosine, and we get that right there. Right? And I think I'd rather you just leave it as an arc cosine. An exact solution is, no, it's an exact solution. It is totally precise. So here we can write that as root 6 over 6. But of course, if you did want to write that as 1.1503, you're welcome to do that as well. But in any event, there is our spherical point. Let's take a look at an equation now. If we convert an equation from rectangular to spherical, we're using the same conversion factors that we have used here, but instead of doing it for a particular point, we'll look at an entire equation all at once. So for example, let's consider something like x squared plus y squared equals to 2. You'll remember this from a previous section. This is a cylinder. It's a cylinder whose generating curve is a circle of radius root 2 on the xy plane, and whose rulings, well, since z is missing here, the rulings are parallel to z. Okay? So here we're going to convert this into spherical. Now you might say, well, wait a minute, wouldn't cylindrical be easier here? Generally speaking, yes. This would be very easy to write in cylindrical coordinates compared to spherical coordinates. But for right now, we're just looking to practice in converting. Right? In application, in practice, if we were using this for something, we would almost certainly not want to use spherical coordinates. But for now, it's just an example of how conversions occur. So here we go. We're going to go ahead and take this. Note that this is almost that expression there, x squared plus y squared plus z squared. That would make converting really simple. Okay, well, let me add z squared there. All right. Well, you can't just randomly add something, right? You'd have to add it to the other side. Okay, well, that's fine. Let me go ahead and write that as x squared plus y squared. I'm going to add a z squared to this side, which means I'm going to add z squared to the other side. Whatever do to one side, do to the other. Okay, now that one's simple. That's just rho squared. Oh, but over here, I know that z can be converted to rho cosine of phi. Okay, so z squared would just be rho cosine of phi squared. Like that. Which you can write as rho squared equals to 2 plus rho squared cosine of phi. Here, these are like terms. We could always combine them. So although this is a correct answer, I believe this textbook would probably have you write something like this. Rho squared minus rho squared cosine of phi equals to 2. You can go ahead and move that over. And then you can even factor out your rho squared. So they would probably ask you to write something like this, or even something like this. Rho squared 1 minus cosine of phi equals to 2. Either of these would probably be what they're looking for. So converting equations from one form to another is basically pattern seeking. You're looking for x squared plus y squared plus z squared. You're looking for arctangent of y over x. You're looking for x or y or z, or any of these should you be going in the opposite direction. Okay. Finally, the last thing for this section, we are going to look at a few simple sketches, because one of the things that we're going to be using this for throughout this course is we want to use these as examples so that we can exercise some of our more challenging concepts. I'm going to learn how to how to find a surface integral. I'm going to learn how to find the flux through a surface. I'm going to figure out how to find volume of three-dimensional objects. And I'm going to find how to use Green's theorem to talk about the connection between the surface and the volume. All of these things are going to require examples. We're going to need to know, okay, here's how this looks with the particular function. And just like in Cal 1, Cal 2, and even before calculus, in algebra, many of our examples benefit some from a visual example. Not that they require the visual to be done, but oftentimes it's a good way to focus your thoughts and try to come up with a strategy. If you can see, hey, this is what this looks like. It looks similar to something that I've seen before. So maybe I want to try it using that technique. So sketching things in the XYZ coordinate system is very useful, just like sketching things in the XY plane has been useful up until now. But since we now have a new coordinate system, well, we're going to want to be able to sketch things in those new coordinate systems. This is not something you need to learn immediately and that's it. You got it and we're done. This is something you'll be exposed to repeatedly throughout this course. This is just one instance, probably the first instance you may have ever seen of sketching something in a system beyond just the rectangular coordinates. So here, our last examples, I'm going to just sketch two not terribly complicated things. I'm going to go ahead and sketch the following. First of all, in cylindrical coordinates, I'm going to sketch the following solid. I want the solid that has a value of theta that's between negative pi over 2 and positive pi over 2. I want R to be bound between 0 and 3. And I want Z to be bound between 0 and R times the cosine of theta. Okay? So here, this is kind of like saying, I want to sketch the solid. In fact, let me do that over here. I want to sketch the solid where x is bound between 0 and 1, where y is bound between 0 and 2, and where z is bound between 0 and, let's say 1, is bound between 1 and x. You could sketch that. Okay. X is between 0 and 1. Okay, so here's my x-axis. When x is equal to 0, I'm at the origin. When x is equal to 1, I'm one step toward us, out of the page, toward us, away from the origin. Okay. Here's the y-axis. Y is between 0 and 2. Okay, well, y is 0 at the origin. Y is 2 steps to the right. So here we want everything between here and here, and between here and here. Well, that's going to be a rectangle. It's going to be a rectangle that's 1 by 2. But this is a three-dimensional object. We're also going to go up above the plane. Our height is going to be a minimum of, you know what? I should say 0 here. Yeah. Otherwise, the drawing wouldn't make sense. So here, z equals to 0. Okay, that means we're going to start at a height of 0. And we're going to go all the way up to, well, notice that's not a constant. If it was a constant, you would just end up with a box, right, with dimensions 1 by 2 by whatever. But here, this height is not just a constant. In fact, it's whatever x is. Okay, well, here x is 0. And in fact, along this entire line, x is equal to 0. Okay, so that means that along this line, you start at 0, and you go up to 0. So that's it. You just stay on the line. Okay, what about over here? Well, over here, x is equal to 1. Okay, it doesn't seem to matter what y is equal to. So here, our height is going to be between 0 and 1. So we're going to go up as high as 1 unit. Like that. What about right here? It looks like x is equal to a half. In fact, along this entire line, x would equal to 1/2. Right? Half of between 0 and 1, it would equal to a half. Okay, so along that line, your z value, your height, will be between 0 and a half. So you'd only go up half as high. Notice that's going to form a slanted line, like this. So this solid would be this, if you've ever seen a really fancy wedge of cheese, like that, notice here you have not just the outer edges, but everything in between. So here this would be the whole wedge of cheese. Here you're looking at the flat surface. The flat surface is sticking up toward us, and the sharp edge of the wedge is right along the y-axis pointing away from us. That would be the sketch of that object. Here we're going to sketch an object similar to that, but instead of x, y, and z, we're going to sketch it in polar coordinates. here, I first worried about sketching the XY plane. I cared about finding, okay, what's down here? Then I said, okay, how high is it? That's often a good strategy. Start by looking at just the r theta plane, because we know how to graph things on the r theta plane. That's the thing we've done since trigonometry. So in fact, if you really need to, go ahead and do it off to the side. On the r theta plane, I want theta to be between negative pi over 2 and positive pi over 2. Okay, well, negative pi over 2 is down here, and positive pi over 2 is over here, from negative to positive. R, well, I want R to be between 0 and 3. So 0 means I stayed at the pole. 3 means I went 3 units away from the pole. So 1, 2, 3. Oh, there we go. That's everything from the pole out to 3 steps with my angles from negative pi over 2 up to positive pi over 2. That's what it'll look like on the flat plane, on the XY plane. So now we just have to worry about what z is equal to. Okay, so on this plane, we want, you can think of this as being like your x and this is like being your y. Now here's your x and here's your y and here's your z. We'd want to go 3 steps toward the x-axis. 1, 2, 3. And this is sweeping out a circle, so this is 3 units in every direction this way as well. So 1, 2, 3, and 1, 2, 3. So it would look something like this. So that's our base. Our object will live above this thing. Okay, so now, how far up is it going to go? Well, it looks like it goes down as low as 0. Okay, so it's going to start here on the xy plane. But it's going to go up as far as, okay, well, that's not going to be flat. It's going to be r cosine of theta. Oh, yeah, but isn't r cosine of theta, isn't that just x? Yeah, this is a way of saying, hey, look, my z is going to go as far as x was. That's exactly what this says. So over here, my x would be 0. Way back here, r cosine of theta is equal to 0. So back here, I'm all the way down to the plane, and I never leave the plane. I go from 0 to 0, right? Because this is x. X is 0 back there. Now up here, x is equal to 3. So my height is going to go from 0 up to 3. Like that. And just like this one did, it's going to go down toward that point. It's going to form like a wedge. Okay. But of course it doesn't do it just along here. It's going to do it all the way down. So this will have this kind of shape along the edge. Okay. To visualize this, imagine you took a soda can, can of soda, right? You went ahead and just took a really sharp knife and just sliced diagonally. That's the object you're getting. And that would include all the space inside. So I guess it would be more like, imagine you took a can of soda or something that's been frozen, right? So you have the cylindrical shape that's solid all the way inside. And you take a sharp knife and you slice. All right, so here you have the base, here you have the height, and the height is going down toward this center. So you took your soda can and you slice from here right into the center, cutting out the bottom. Once again, this is all the stuff in between, so this would actually give you everything inside of that object as well. You don't just have to sketch in rectangular or cylindrical. We can also sketch in spherical coordinates. In spherical coordinates, let's go ahead and sketch the solid that's defined where theta. Let me go ahead and state these the way, the order that we usually use. So let's say 0 is less than or equal to rho is less than or equal to 1. Okay, so we're going to have a distance away from the pole that's between 0 and 1. So we're going to stay inside of a sphere of radius 1, which incidentally is called the unit sphere. Just like the unit circle, that's the unit sphere. We're going to take our theta to be between 0 and 2 pi. And we're going to take our phi to be between pi over 4 and pi over 2. All right, so let's go ahead and sketch that graph. Okay. All right. Phi is between 0 and 2 pi. Okay, that means we're going to go all the way around. Okay, so here's 0. We're going to go all the way around to 2 pi. We want rho to be between 0 and 1, which means we want to start from the pole, and we want to go out as far as the unit sphere. Now, we may not take the entire unit sphere, but that's the maximum. So here, let me draw a sphere of radius 1. So that's where it would intersect the xy plane. And of course, it would go above the xy plane. Like that. Since we know we're going to stay inside of this unit circle, I suppose I should, well, since we know we're going to stay inside of this unit circle, everything else can be contained within that. Here, theta between 0 and 2 pi, so we know we're going to go all the way around. That means we're not going to want just like a quarter of the sphere or half of it. We want the full all the way around. However, here I really should be drawing the full sphere, right? It does go down as well, like that. Here, remember, phi is another angle. Phi equals to 0 is pointing up along the vertical axis here, up along z. So, if phi equals to 0 here, phi would equal to pi over 2, well, that would be 90 degrees. Now you say, well, in what direction? Well, it's actually in every direction. So for now, it's sufficient to pick one direction. And I'm going to make it easy on myself. I'm just going to go in the direction of the y-axis, because that's easy to draw here. So, if theta is equal to 0, that's pointing straight up. If theta is equal to pi over 4, that's pointed 45 degrees, pi over 4 radians this way. Really, it's in every direction, but this is good enough for now. And then pi over 2 would be in this direction, where you're facing along the y-axis, or the x-axis. But again, keeping it easy on myself. So I don't want up here. I just want this part between pi over 4 and pi over 2. So what that means is I want to stay inside of this unit circle. I want to stay inside of this unit sphere, rather. I want to go all the way around inside of this unit sphere. However, I don't want to take this part. Imagine taking this and spinning it. That's what theta does. It's going to take this portion here, this sort of little wedge, and spin it around this way. So what that means is we're going to want everything that's here spun all the way around the pole. So that means we're going to take the sphere, we're going to lop off the bottom half. So here this does have a flat bottom. It only goes as far as the plane. It doesn't extend underneath that. And notice that there is this wedge that's empty. This is hollow. There's nothing in here. So I'm going to go ahead and draw this in now with pen. You're going to have this circle that's on the XY plane. You're going to have what looks like the upper half of the unit sphere, but not quite the upper half, because here you're going to have this part cut out. Like that. So it's going to be this stuff in here. Just like that. So So this would be our solid. Essentially, take a ball, cut it in half so that it's got a flat bottom. It's resting. The flat bottom is resting against the ground. Okay, so now you just have the upper half of a ball. Now take a cone and just press it into the ball until the tip of the cone touches the ground, right through the middle. All right. What's left of your ball, that's the shape we have here. These will sometimes take a bit of effort to get used to. Whenever you're dealing with rectangular coordinates, start by graphing just x and y first so that you have your base, and then worry about how far up or down you're going. Same thing with cylindrical coordinates. Graph your r and theta first so that you have your base, then worry about how far up you're going. With spherical, it's a little different. What you want to do is you want to start with phi, so that it gives you an idea, okay, I'm inside of this sphere. I'm inside of the sphere of unit 1, the sphere of radius 2. I'm between the sphere of radius 1 and the sphere of radius 2. Something like that. I'm within this shell. And then, from there, consider phi. Okay, phi tells me how far from the z-axis I'm considering. Oh, here I'm considering not from 0, which would be facing straight up, but from pi over 4 to pi over 2. So within the unit sphere, I'm considering this portion here. And then finally, theta, that's going to spin you around. From 0 to pi over 2, oh, you're taking that little wedge right there and you're spinning it all the way around. If it was just from 0 to pi, oh, you're only spinning it halfway around. So here you might consider rho and phi first, and then finally theta. But that is it for our examples, and that brings us to the end of our section. If anybody has any questions, comments, or problems, please make a note of those. Note that this is not the last time you see sketches like this. This is meant as an introduction. We will see more of this throughout the coming sections and coming chapters. But for now, that brings us to the end of this video. If anybody has any questions, please let me know, and I hope everyone has a nice day.